All right, today we're going to go through chapter 15. We'll probably merge a little chapter 16. The test will be posted by Wednesday. I'm also going to post the video of how to fill out the report sheet. That will be in by Wednesday as well. I'll send an email when they go out. All right, so chapter 15 is acid and bases. Some of these things we already know. Some of these things we do not know. There's three concepts of acid-base. There's Arrhenius, Bronsted-Lowry, and Lewis. And we will do all of them, except our main focus is going to be on a Bronsted-Lowry concept. So here are the three different concepts. Arrhenius concept, which just means you're going to put a substance in water. If it's an acid, it increases the H3O plus concentration. If it's a base, it increases the OH minus concentration. All right, so that is the definition of the Arrhenius concept. Bronsted-Lowry, it's just all about proton donors. So acid donates a proton, base accepts the proton. That's 90% of the acids and bases that we're going to talk about are going to be the Bronsted-Lowry concept of acid-base. Lewis concept, we have a chapter on formations of complex ions. So we're going to talk about a lot of Lewis bases and Lewis acids in that chapter. Organic chemistry does a lot of Lewis acids, Lewis bases. Very strange definition for the Lewis acid, Lewis base. It's not about H3O plus, it's not about OH minus, it's about electron pairs. All right, so an acid is an electron pair acceptor, so that's a Lewis acid. A Lewis base is an electron pair donor, so it's a completely different type of concept. All right, so this chapter focuses mostly on the Bronsted-Lowry concept of acid and base. And note here, if I'm going to write a lot of H plus, I'll write some H3O plus, but most of my dealings are with H plus. It doesn't matter. H plus, H3O plus are exactly the same thing. All right, so an H plus is taken off with water, so it technically should be written as H3O plus, but it is accepted as H plus. It's easy to write H plus, and so that's what I normally write for my H plus. I will write both, but most of the time I will write H plus. All right, and so on the PowerPoints, it has the definitions. I went through them quickly. It's there. Arrhenius acid, you throw it in water, increases H3O plus. Arrhenius base, you throw it in water, it increases OH minus. Bronsted-Lowry, all right, so Bronsted-Lowry is a acid base is about proton donors and proton acceptors. All right, so this picture is showing that a proton from H3O plus, I don't have to write it 4 times, but whatever, a proton is going to the NH3. All right, and so this is your proton donor. All right, so why is H called a proton? Well, if you look at hydrogen, and H plus is called a proton because when you count the protons, neutrons, electrons, periodic table, hydrogen is number 1. That means it has 1 proton. The mass number is 1, and so there are 0 neutrons. The total protons, neutrons is 1. It's H plus, and so it also has 0 electrons. All right, so when you talk about H plus, that's why it is called a proton, because H plus only has a proton. All right, so you'll hear H plus, you'll hear proton. That is the same thing. All right, and so we're going to do H plus, a proton donor, and a proton acceptor. So the H comes from the acid and goes to the base. All right, and so when you lose an H, you have H2O. When you gain an H, you have NH4 plus. All right, and so this is your acid, and this is your base. Now we have equilibrium, so we are going to have a lot of equilibrium. On the right side, you also have an acid and a base. All right, so on this side, to go back the other way, the NH4 is going to have to give the proton to the H2O. All right, and so this is going to have to give a proton to the H2O in order to make it H3O plus. So on this side, here is your acid, and here's your base. Now, the book likes to call the ones on the right the conjugate acid and base. That's fine. I like to draw my lines from the acid on this side to the base on this side, and they are conjugates. All right, so what is a conjugate? Well, it simply differs by 1 H plus. One H plus. If it differs by more than 1 H plus, they're not conjugates. So a conjugate acid and a base, it's always going to be an acid and a base. Conjugate acid base is always going to differ by 1 H plus. And so you see from here to here, these are also conjugates. They differ by an H plus. So H3O plus, H2O, that differs by an H plus. NH3, NH4 plus, that differs by an H plus. And so they are conjugate acid-base pairs. The acid is always the one with one more H. So H3O plus has one more H than H2O. The one with the more H's is the acid. The one with the one fewer H is the base. Conjugate acid base always differ by 1 H plus. The one with the extra H plus is the acid. The one that doesn't have the extra H plus is the base. All right. So they go through that. They draw their lines. Note how they do it in the book, which is fine. The things on the right, they call the conjugates. All right. And so here is the conjugate base. Because you start on the left, you go to the right. So if H3O plus is your acid, the conjugate base, which means it's going to have one less H, is going to be H2O. I usually write conjugate over the arrow. It makes no difference. But you have to connect those two things and call them a conjugate acid-base pair. All right, so if we have our two problems here, again, the box means it's equilibrium. So you've got to figure out what's going on. And this one is more difficult because you have this compound that starts with an H and this compound that starts with an H. And definition is acids start with an H, all right, but here we have an ionic compound, all right, and so this is not going to be called an acid. This is actually bicarbonate. It's an ion. All acids are neutral. Now, bicarbonate could be acidic. In bicarbonate's case, it's not. Its pH is around 8, and it's a base. But if we did the bisulfate, that is very acidic. So it's hard to tell. You can't really tell when it's an ion. When it is an aqueous, starts with H, we know that is an acid. In this case, they give us the products, and they would have to in this case. Well, they wouldn't have to in this case, but in many cases, they would have to. All right, because what we're going to see is that the HCO3 minus can act as an acid or it can act as a base. So in this case, you see we're getting F minus. So this hydrogen is being donated to this bicarbonate. So here's your acid. All right, because it is donating the hydrogen, and then this one's taking the hydrogen, and so it's the base. Proton donor, proton acceptor. All right, if we go to the other side, now we have no ambiguity. So we have only one possible acid. This one has 2 acidic hydrogens. This one does not have any hydrogens. All right, and so this is your acid, and this is your base. So the left side is going to have an acid base. The right side is going to have an acid base. Again, the book will call the ones on the right side the conjugate. And so you connect the acids and bases. So here's the base on the left, acid on the right. They will always differ by 1 H plus. They are conjugates. So here's the base and there's its conjugate acid. All right, and so for the HF, here's the acid and here's its conjugate base. Again, the conjugates are usually what are on the other side, on the product side. All right, so here's another one. Again, bicarbonate, but this time we're putting it in OH minus, which is a strong base. All right, and so when we put that in with a strong base, they're going to give us our products, and we get H2O. And so this one is accepting the H from the bicarbonate ion. And the bicarbonate ion is donating its H to the OH. So this is your base, and every time you have OH minus, that's your base. Anytime you have H plus, that's your acid. All right, and so this is your acid. And so on the other side, again on this side, there's only one that can be the acid. Now we know water is neutral, but again, water will act like an acid in some cases. It will act like a base in some cases. In this case, it's going to act like an acid because it's going to donate its hydrogen to the CO3 minus 2 to make it HCO3 minus. And so your CO3 minus 2 is going to accept that hydrogen, so it's a base. And then we just connect the acid on the left side with the base on the right side. They will always be conjugates. They will always differ by 1 H plus. And the one with the one less H plus is the base. The one with the one more H plus is the acid, always. And here's your conjugate acid-base pairs. OH minus, H2O differ by 1 H plus. All right, so you're going to be given a reaction. You're going to have to label the acids and bases and state which ones are conjugate acid-base pairs. All right, so again, conjugates are differing by 1 H plus. All right, so if I go back here, I said it, but I will circle it. So when you have your HCO3 minus, notice in this one, it's a base. Notice in this one, it's an acid. Water will do this all the time. It depends on what you put it in. Bicarbonate will also do this. Bicarbonate is a good buffer. It'll neutralize an acid. It'll also neutralize a base. So it's a good buffer. We'll talk about buffers in the next chapter. But in this case, if you throw it in with an acid, the bicarbonate acts like a base. If you throw a base in with the bicarbonate is going to act like an acid. All right, so water does this all the time, and that is called an amphoteric species. All right, so it will depend on your the other reactant. If you throw in a strong acid, it's going to react like a base. If you throw in a strong base, it's going to act like an acid. All right, so they can act either as an acid or a base. All right, so here they call it an amphoteric species. Here they call it an amphiprotic species. All right, so I will accept either one of those, meaning amphiprotic means it can donate a proton or accept a proton. Amphoteric means it can act as an acid or a base. So that's the same thing. I will accept either answer for that, amphoteric or amphiprotic. Ambidextrous means you can do right hand or left hand. All right, so this is either can act as an acid or a base. All right, so the Lewis concept, I said, is a lot different than any acid-base concept that you probably know about. It has nothing to do with pH. It has nothing to do with H plus, OH minus. It is all about electron pairs. All right, so a Lewis acid will accept an electron pair. A Lewis base will donate an electron pair. So it's a completely different type of acid-base concept. So here, if you look at your BF3, what you will notice on your BF3 is it does not have an octet. It only has 6, and that's fine, but most compounds would like to have an octet. Your Lewis base, every time you have a Lewis base, which means it is an electron pair donor, which means if you don't have an electron pair, you cannot be a Lewis base. And I'm talking about the central atom, all right? So it is the central atom. The BF3 has electron pairs on the fluorines, but it is about the central atom that we are looking at where the reaction is occurring. All right, and so the BF3 could not function as a Lewis base because it doesn't have an electron pair on the central atom. All right, so your nitrogen has an electron pair on the central atom, and then you would draw the arrow. The arrow always comes from the electron pair, and it will go to the Lewis acid. And that's going to form a bond. All right, so this is one way that you can show a bond. You should be consistent. They're not being consistent. They're showing lines for all the other bonds, but not a line for that one. That should be a B and an N. It should show a bond there. All right, and so what we do see is that boron is neutral on the left because boron is in column 3, and it should have 1, 2, and 3 electrons, which it does. And it shares with the 3 electrons of fluorine. All right, so now over here we have 1, 2, 3, 4 electrons because this bond is boron to nitrogen bond. All right, so now it has 4. It's only supposed to have 3, so it's minus. Nitrogen should have 5. 1, 2, 3, and then the lone pair 4, 5. Now it only has 1, 2, 3, and 4, and so it is plus. And so your boron is minus formal charge. Your nitrogen is plus formal charge. All right. So when you do a Lewis acid base making a bond, then you're going to have some formal charges to put in there as well. All right. So we're going to do this a lot when we get to our metals with our Lewis bases. We're going to have metal cations. Lewis bases are going to attack it. Once the Lewis base is on there, then it is called a ligand. All right, so a Lewis base must have an electron pair to be a Lewis base because it's an electron pair donor. All right, so here is one of the, so this is going to be in, I forget what chapter, 18, 19 maybe. So it's going to be an equilibrium. We're going to do ones just like this. All right, and so here is where when you do a Lewis acid, Lewis bases, you've got to be able to draw a Lewis structure, which is why it's called a Lewis acid and a Lewis base, because if you can't draw the Lewis structure, you cannot determine if it could be a Lewis acid or a Lewis base. So when you draw your Lewis structure, you see that your NH3 has an electron pair. Ag plus, that's it. That's Ag plus. There's no electrons around it. All right, and so you have 2 NH3s. And note how a Lewis acid, Lewis base makes a bond. It makes a bond by both electrons coming from the same atom. All right, and so when both electrons come from the same atom, to make a bond, that is called a coordinate covalent bond. All right, and so this is not a typical type of reaction. This is going to then give you your complex ion, Ag, NH3, sub 2 plus. All right, so on the left side, these NH3s, this is a Lewis base because it is electron pair donor, Lewis base. And then your Ag plus is your Lewis acid because it accepted them. All right, now, once the NH3s are connected to the metal, then they are called ligands. All right, so that will be important when we get to later chapters. Right now, it's important to know, identify the Lewis acid and the Lewis base in this reaction. All right, but when we get to chapter 18 or 19, when we do these complex ion formations, it's a Lewis acid as a reactant, but as a product, when it's connected to the metal, then it is called a ligand, or it can also be pronounced ligand. All right, so we're going to have questions like which one is the stronger acid? Some of those will be easy, like HCl versus HF. All right, so this would be a very easy question. Which one is more acidic? Well, it's easy because you have to memorize your 6 strong acids. So we did it last semester. We're going to have to do it again. 6 strong acids. You have to know them. You have to know that HCl, HBr, HI, HNO3, HClO4, and then the only polyprotic is H2SO4. So there are your 6 strong acids. All right, so when you have a 1, when it says which one is stronger, and this one is a strong acid because you have memorized the 6 and it's one of them, and you have memorized the 6, that's not one of them. And so if you're not a strong acid, you're a weak acid. All right, so if the question was which one's stronger, HCl or HF, that would be an easy question as long as you know your 6 strong acids, because that one's strong, that one's not. Well, obviously the HCl is the stronger acid. What is it meant to be a strong acid? What it means is it is 100% ionized. It has nothing to do with how corrosive it is, how dangerous it is. If you say stick your hand in HCl or HF, I'll put it in the HCl. HF is much more corrosive, eats glass. So anyway, so when you say strong acid, doesn't mean it's dangerous, more dangerous than any other acid. All right, so it just means that it's 100% ionized. All right, so then it could be which one is, okay, so this one is, which is stronger, is a stronger acid. All right, and so HCl. Or I could have said, which is a stronger base, Cl minus or F minus. All right, and so that's the same question. It's the same question because here we go. The stronger an acid, the weaker its conjugate base. You have to know that phrase. And then the question of HCl versus HF, which one's a stronger acid, is exactly the same question as which one's a stronger base, Cl minus or F minus, because we see that that is the conjugate base of those 2 acids. Conjugate means differs by 1 H. HCl is the acid, Cl minus is its conjugate base, so that's a conjugate acid-base pair. Same with the HF. It has 1 more H than the F minus. It's a conjugate acid-base pair. All right, so the stronger the acid, the weaker its conjugate base. So the HCl is a stronger acid, and so the Cl minus is a weaker base. And so F minus, if that's the weaker base, this has to be the stronger base. All right, and so we use the weaker, stronger. We're comparing it to something. Neither one of those is a strong base, but the F minus is a stronger base than FCl minus. All right, so you will have to determine that, which is the stronger acid, which is the, and then of the 2 acids, and which is the stronger base. And you're going to do that by knowing this rule up here. The stronger an acid, the weaker the conjugate base. Or, of course, the weaker an acid, the stronger the conjugate base. So you could have just said HF is a weaker acid, therefore F minus is a stronger base. Yes, that's the same. That's what we wrote. Okay. All right, the next slide gives us our relative strengths of acids. This is not going to be given on the test because it's going to be a question on the test, which one is the stronger acid? And, well, you're not just going to look at it and get the answer. You're going to have to know why. Here is a very interesting sequence of acid strengths. All right, so you'll notice that your HI of the 3 strong acids in that halogen column. The strongest is HI, the weakest is HCl in that column. All right, and so that is interesting. So what we can come to the conclusion of that right there is that when we go down the periodic table, we get more acidic. So the larger the atom attached to the H, the stronger the acid. All right, right here. All right, so going down a group in the periodic table, that means the size is getting bigger. All right, so as you go down, the atom gets bigger. All right, and as the atom gets bigger, the more acidic it becomes. And so here you have your H connected to an I. Here you have your H connected to a Br. Here you have your H connected to a Cl, and here you have your H connected to an F. And so the atoms are getting bigger. So I'm just writing the letters bigger, but that just means you're going down the periodic table and they're getting bigger. All right, and so when you have an H connected to a giant atom, an atom down the periodic table, that H is easily released, and that is a stronger acid, which means it ionizes very fast and 100% ionization. And so that is one of the rules. If you now are going to compare H2O, which we know is neutral, and the one underneath it, H2S, all right, so S is bigger, and it's going to be more acidic. Well, water is neutral. It's not acidic at all. And hydrosulfuric acid is acidic. And so that makes complete sense. This one's neutral. This one's an acid. So as you go down the periodic table, we go down to the next atom, down to the next atom. All right, so it's getting a stronger and stronger acidity as you go down a column. All right, let's go to the next slide, which is going to go across the periodic table. All right, so we just had HF, it's a halogen, and then to the next to that, to the left of that is O, which is H2O. Then to the left of that is nitrogen, except remember, we don't write nitrogen H3N, we write nitrogen NH3, and there's a reason for that. All right, so just by knowing these three compounds, HF, that is an acid. Hydrofluoric acid. H2O we know is water. It's neutral, pH 7. So we know that this has a low pH. HF does. All right, it's an acid. H2O we know is pH 7. And if you know ammonia, maybe you do, maybe you don't. The reason why we don't put the H's in front is because ammonia is not an acid. It's a base. All right, and so ammonia is a base. Water is neutral. And HF is an acid. And so that's the trend on a row. So as you go to the left, from left to right, as you go to the right, from left to right, all right, so from nitrogen to oxygen to fluorine, you're going to get more acidic. You go down another row, the exact same thing. You go from phosphorus, which is, you go pH3, you go to H2S, you go to HCl. All right, so you know that the HCl is a strong acid and those other two are not. Again, same trend. As you go to the right, you're going to get more acidic. And this is less acidic. All right, so you increase acidity as you go across the periodic table. You increase acidity as you go down the periodic table. All right, so another interesting thing is we just went through the HCl strong, and then HF is weak. And then as we went down, it got more acidic. And then you have your 6 memorized strong acids, one of them being HClO4, and that was actually on the top of the list of strong acids, stronger than any of the others. All right, which is interesting because what's not listed is an HBrO4 or an HiO4. This is a weak acid. This is a weak acid. How do I know that? Well, it's not one of the 6 memorized strong acids. This is one of the memorized strong acids. All right, so this is a strong acid. All right, so it seems like a contradiction. We just said as you go down the periodic table, it gets bigger. Remember what was attached to the H. When we went down the periodic table, the atom attached to the H kept getting bigger, bigger, and bigger, which is not the case here. Because an oxy acid, you have an oxygen and you have an acid. All oxy acids, the H is attached to the O. And so the H is attached to the O. And every one of these, the H is attached to the O. It's not attached to something giant. It's attached to the exact same thing on all of those. All right, and so when you have your HClO, it is just more polar because chlorine is more electronegative. All right, and so your HClO4 is then your most acidic. It has, so the next slide is going to show the more oxygens that you have, the more polar it's going to get, and the more acidic it's going to get. And you'll know this is an easy one to know because this is a memorized strong acid. These are all acids. They are not strong, so they are all weak. And so as you add oxygens, you get stronger and stronger and stronger. In the case of HClO4, that one is a strong acid. You would have the same trend in HBRO, HBRO2, HBRO3, but HBRO4 is not a strong acid. It's not one of the memorized 6 strong acids, but we know it's stronger than the HBRO or the HBRO2 or the HBRO3. So the more oxygens that you have, the more acidic. Now again, these are oxyacids. The H is attached to the O in every one of these. Then just a common sense rule, the more H's, more acidic. All right, so if you have 2 H's and you have 1 H, this is basically the rule of conjugate acid bases. These are conjugates. All right, and so the acid is the one with the extra H. The base is the one with the one fewer H. All right, and so they are conjugates. And so, of course, the one with the extra H is the acid, more acidic than the one with the one fewer H, that is the base. So that one is just a common sense. More H's, more acidic when you have your conjugate acid-base pair. All right, so when we do reactions, they are going to be equilibrium reactions. And what is very important, that's a very important statement right there. A reaction will always go in the direction from stronger acid to weaker acid and from stronger base to weaker base. And I'll make it even simpler than that, is that when you do a reaction, you're going to have one side is going to have your stronger acid plus stronger base. All right, and it's going to go to weaker acid, weaker base. All right, so the stronger acid, stronger base are always on the same side, whether it's on the left side, whether it's on the right side, always on the same side. Your weaker acid, weaker base, always on the same side. So you only need to know one of these 4. If you started a reaction and you had HCl, you know that's a stronger acid because unless you use another strong acid. So let's say you have HCl and on the other side is not one of the 6 memorized strong acids. All right, so you know that's a stronger acid than a weak acid. And so then you know that that's a stronger base, and this is the weaker base, and that's the weaker acid. Stronger acid, stronger base, always on the same side of any acid-base reaction. It can be a reactant side, be a product side. The strongers are on one side, the weakers are on the other side, always. All right, so here I see, well, I know 2 things in this one. All right, so if you look at this reaction in equilibrium, all right, so H3O plus, well, that's a strong acid. And OH minus, well, that's a strong base. All right, so in this case, I knew 2 of them. All right, so this, of course, is weaker, and this is weaker. Acid and base. All right, so on the left side, they're both neutral. H3O plus is obviously acidic. OH minus is obviously basic. All right, and so they're stronger acid and stronger base on the right. Again, the weaker will always be on one side, the stronger will be on the other side. All right, and so this, if we write the Kc, the equilibrium constant for this, we get that our Kc is equal to the concentration of H3O plus, and I could have wrote that as H plus, concentration of OH minus. Now, since this is the equilibrium constant for water, we don't call it Kc anymore. We get specific. This is the equilibrium constant for water. All right, and so it's Kw. And what we also know is at 25 degrees Celsius, it's always the same number. So it's a constant. 1.000 times 10 to the minus 14. All right, so Kw is a constant. It's going to be given on the exam. You don't have to memorize it, but we're going to use it so many times that you will have it memorized. Kw is 1 times 10 to the minus 14. And that is the concentration of H3O plus times the concentration of OH minus. And what I did leave out is why didn't I divide by water? Well, hopefully you see that water is a liquid, and solids and liquids do not go into your Kc expression, only aqueous and gases. And so I stuck in the H3O plus, I stuck in the OH minus, the waters are not included. If you did this with just H2O going to H plus and OH minus, that's the exact same reaction. And this time you have Kw, it's 1 times 10 to the minus 14. But when you do this setup, water, of course, is a liquid. Anytime you have a charge, you have an ion. All ions are aqueous. Many times I will not write aqueous. You need to know that if I put a charge for it, a plus or a minus, it is aqueous. All ions in this class are aqueous. All right, and so this could be written as H plus concentration times OH minus concentration, because this H2O liquid does not go into the expression for Kc. And now this Kw is Kc, but it is special. It is for water. And so we put Kw, and that's a constant, 1.000 times 10 to the minus 14. All right, and so that's this. All right, your Kw is a constant, 25 degrees Celsius. And if we increase the temperature, the value of Kw will increase, more will ionize. We're going to stick at 25 degrees Celsius. We did our changing temperature things. We are going to stick with 25 degrees Celsius. All right, so here we have our strong acid and our strong base. All right, so we had our 6 strong acids, our 6 strong bases. You've got your NaOH, KOH, LiOH, and then you've got your calcium hydroxide, your strontium hydroxide, and your barium hydroxide. All right, so lithium, sodium, potassium, and then you go over next to the potassium, calcium, strontium, barium. So those 3 down, then over, and then 3 down there. That's your 6 strong bases. Again, there's nothing special about this except to know that it just means that it is 100% ionized. All right, that's all it means by the strong bases here. And that's going to be important because we're going to do our reaction here. So the first one, we have HNO3. Now we know that this is a strong acid. And so we don't write an equilibrium. We know it's 100% ionized into H plus and NO3 minus. We can do the same ice, except it's not ice. It is ICF. There's no E, right? There's no equilibrium. It is final. So here we started with 0.15. Here we started with 0, 0. It's going to go to the right, minus x plus x plus x, and it goes until the left side is gone. It's 100% ionized. Everything goes to the right. All right, and so finally we're going to have 0 of our strong acid, which means our x was 0.15. And so we have 0.15 of H plus, we have 0.15 of NO3 minus. All right, and so our concentration of H plus is 0.15 molar. All right, so you're going to have terms, and you need to know what they mean. The hydronium ion is H3O plus. An easier term would be the hydrogen ion, except they rarely use that. They call it the hydronium ion. You have to know if they're asking for the hydronium ion. Don't get the problem wrong because you don't know what the hydronium ion is. All right, that is an H3O plus. Of course, if you give the hydrogen ion concentration, great, because that is exactly the same thing. H3O plus is the same thing as H plus. And then we already memorized hydroxide in the first semester, so you all know hydroxide is OH minus. All right, and so if they're asking for a concentration that starts with an H, then it's not hydroxide. Well, then it's going to be the hydronium, and you want the H3O plus. Hydroxide is only called hydroxide. There's no other name for it. That's hydroxide. You know that one. If there's some hydra name you don't know, it is the H3O plus. All right, hydronium ion is H3O plus. Hydrogen ion, H plus. All right, so don't miss the problem because you don't know what the hydronium ion is. All right, so this would be 0.15 molar, and there's your answer. All right, and that is when you have a strong acid. Now, the next one is calcium hydroxide, which is also 100% ionized. All right, single arrow, calcium plus 2 and 2 OH minus. All right, so initial here is 0.01, 0 and 0. All right, and this is not ice, this is initial change and then final, because it's 100% ionized. So minus X plus 2X. And so here, you don't have 0.01 minus X, you have 0 because it's 100% ionized. It's gone. So now we know that X is 0.01. So we have 0.01 and we have 0.02 molar. That is our concentration of OH minus, the hydroxide ion. All right, except we only answered one of the questions for each one. And this could also be a problem. When it asks for the concentrations of this and this, that means you have to give two numbers, not just the one number. And so now we have to know that we have our Kw, which is equal to 1.000 times 10 to the minus 14. And that's equal to our H plus concentration times our OH minus concentration. And we have this in every single problem, because every acid is aqueous, and that means that every time we have an acid-base reaction, we have water. Every time we have water, we have Kw. And so we will always have an H plus concentration and an OH minus concentration. If your H plus concentration is higher than your OH minus concentration, you're an acid. So in part A, our H plus is 0.15. Our OH minus is going to be extremely small. We will calculate it. For the OH, for the calcium hydroxide, that's a base. Our concentration of OH minus is 0.02. The concentration of H plus is going to be extremely small, and we will calculate that. All right, so I'll go up here and write, so 1 times 10 to the minus 14. I'm going to give everything to 2 sig figs when I'm done, because the problem all has 2 sig figs in it. All right, my H plus is 0.15 for part A. I need to know what my OH minus concentration is. So you just get your calculator and you divide both sides by 0.15. And you get 1 minus 13, 1 over 3/2. You get a 6.7 times 10 to the minus 13, but no, it's 1 divided by that. 0.67. Minus 14, is it 6.7 times 10 to the minus 14? Yeah, okay. All right, so 6.7 times 10 to the minus 14, that is your OH minus concentration. All right, we're going to do the same thing for this one. Now we have the 0.02 molar. And so 1 times 10 to the minus 14 is equal to my H plus concentration. And now my OH minus in this one is 0.020. All right, and so now I have 2 times 10 to the minus 2. I got minus 12.5 times 10 to the minus 13. So 5.0 times 10 to the minus 13 should be what you get when you push your buttons on your calculator, I'm hoping. All right, so you can see this H plus concentration. Very small, 5.0 times 10 to the minus 13. Extremely small number because this is basic. All right, so when your H plus concentration is greater than your OH minus concentration, then you're an acid. If your OH minus concentration is greater than your H plus concentration, then you're a base. right? And of course, if they're equal, then you are neutral, pH 7, and you are water. All right, so yeah, 6.7 times 10 to the minus 14, 5.0 times 10 to the minus 13. Yeah, so anyway, it's all worked out nicely for you in here. And then again, all right, so I just compared the concentrations. Remember that when you have water, pure water, you have your Kw, which is equal to your concentration of OH minus concentration of H plus, doesn't matter what order you put them in, is 1 times 10 to the minus 14. They are exactly the same concentration. All right, and so you simply, if you want the concentration of H plus, it will equal the concentration of OH minus, which means you had to take the square root of that number. So that means it is 1.0 times 10 to the minus 7 molar. All right, so for pure water, your H plus concentration is exactly the same as your OH minus concentration. It is neutral, and it is 1.0 times 10 to the minus 7. All right, so now we're going to take and get our pH number. So pH is going to equal to the negative log of your concentration of H plus. Remember, or negative log of H3O plus. H plus, H3O plus, the same thing. All right, so for water, we already know the number. It's neutral, it's 7. All right, and so when you have your chart here, you're going to have pH of 7 right here. This is a pH scale. When you're less than 7, you're an acid. If your pH is less than 7, you're going to be acidic. If you are greater than 7, you're going to be basic. All right, so 7 is the neutral pH number. If you are higher than 7, you're a base. If you're lower than 7, you're an acid. If you're doing concentration of H3O plus, 1 times 10 to the minus 7, that's when you are neutral. If you have a higher concentration than that, then you are an acid. If you have a lower concentration than that, then you are a base, as we saw in the previous answer, where we had a high concentration of H3O plus and extremely small concentration of OH minus. That is an acid. When you multiply your H plus and your OH minus, you always get Kw. All right, let's see. Let's go. Let's go to this one. All right, so let's do 0.10 molar HCl, and I want to calculate the pH. And I'm also going to do 0.10 molar HF, and I'm going to calculate pH. All right, so when you get this problem, there can be a lot of different questions. One could be calculate the pH. One could just be predicted. All right, so could be which has the lowest pH. Give the strongest conjugate base. All right, so which has the lowest pH? So you basically, what is that saying? That says which one is the stronger acid. So you have to be able to convert problems into the same problem. So lowest pH means most acidic, which means which one of these is a stronger acid? Well, this is an easy question because HCl is one of the 6 memorized strong acids. HF is not. All right, so HCl is going to have the lowest pH. When we calculate those two numbers, we better get a lower pH for HCl because it is a stronger acid and will have a lower pH. All right, give the strongest conjugate base. Remember, the strongest conjugate base comes from the weaker acid. So the weaker acid gives the stronger conjugate base. All right, so if you know that, then, well, you already answered that. You said HCl is stronger. Well, obviously, HF is weaker. So the weaker acid is HF. The conjugate base of HF is F minus. Right? And so that's how you would work a problem like that. Instead of, you don't want to memorize everything, you just have to be able to get the stronger acid, stronger base, or stronger acid between the two, and know the rule. The stronger the acid, the weaker the conjugate base. All right, so let's calculate our pHs. All right, we have enough information to calculate the pH of the HCl. We do not have enough information to calculate the pH of HF yet. All right, so we have HCl. We know it's a strong acid, not equilibrium, 100% ionized. We do our initial change and final because it is a strong acid. We started with 0.10 molar, 0, 0. It's going to go to the right until HCl is 0. Use the coefficients, plus 1x, plus 1x here, plus 1x here, minus 1x coefficients. So final, it's 0. It's 100% ionized. We don't have any left, which means that x was 0.10. And so 0.10 molar, 0.10 molar. And so your pH is equal to the negative log of your H plus concentration, which in this case is 0.1. And so your pH is equal to the negative log of 0.10 molar. So when you push the buttons, you get a pH is equal to 1.00. All right, so sig fig rules. It's a strange rule when you're doing pH. We're not going to learn that rule. 90+% of the time, you work all that rule of sig figs for the pH, and over 90% of the time, the answer is 2 decimals. So all pHs give to 2 decimal places. All right, always 2 decimal places. That could be 2 sig figs, that could be 1 sig fig, it could be 3, it could be 4. Rarely would it be 5, but again, just like your molar masses that you give to 2 decimal places, it depends on what the molar mass is. If it's hydrogen, it's only 3 sig figs. If it's carbon, it's 4 sig figs. If it's lead, it's 5 sig figs. It's always 2 decimal places. Same for your pHs. We're also going to have pOH. It will also have 2 decimal places. We're also going to have pKas. We're going to have pKbs. All right, these are all 2 decimal places. All of these numbers are going to be given pKw. All right, so pK whatever is going to have, or pH or pOH, they're going to have 2 decimals. All right, so now we're going to find the HF. And I said we didn't have enough information for HF because HF has an equilibrium because it is a weak acid. So all weak acids are going to have equilibrium. All strong acids go 100% to the right, 1 arrow to the right, left side will be 0. All right, and so here we do ice, initial change and equilibrium, because now it's a weak acid. All weak acids have equilibrium, 0.10, 0, 0. To the right, you can't have zeros, so minus x plus x plus x. At equilibrium, 0.1 minus x, x, and x. The information that you need to solve this is you got to go to the chart, and the chart is going to have not a Kc, but the expression is Kc. So that is the concentration of H plus, concentration of F minus over the concentration of HF. All right, so remember that all acids are aqueous, all right, and all ions are aqueous. And so all of these are going into the expression for Kc. If you put water and H3O+, water is a liquid, does not go into Kc. So it would be exactly the same expression, except it would be H3O plus F minus HF. Again, H plus, H3O plus are the same. This is the ionization of a weak acid. When you have the equilibrium constant for the ionization of a weak acid, we don't call it Kc anymore, we call it Ka. A means ionization of a weak acid. It is exactly the same as Kc. We're just designating that, yes, this is exactly the same as Kc, but this is for a weak acid. And so we are calling it Ka. All right, so we look at the Ka chart for HF, and we find that this Ka is equal to 6.8 times 10 to the minus 4. What else you will notice about all Kas are all of them are small. All Ka values are small numbers, which is great for me because I like to do successive approximations. So for all of these, you can do successive approximations because x is therefore small. All right, and so you can neglect your x, you plug it back in until you get the same answer twice. You can do that for all of your Ka questions. All right, we could have predicted that as well, but if we wanted to predict it, we would have to write it into the other form, which is HF plus H2O. Now we have aqueous HF. Now we have liquid H2O. And that is in equilibrium with H3O plus aqueous and F minus aqueous. All right. So this equation and the equation above is exactly the same equation. You will get exactly the same answers. You will do ice exactly the same way. It is 0.10 molar. Nobody cares about H2O liquid in an equilibrium. It is not part of the equilibrium expression. It is a pure liquid. Liquids do not go into your equilibrium expressions. 0, 0, so minus x plus x plus x. 0.1 minus x, x, and x. All right, and so your Kc is the exact same thing because it started off saying Kc. Okay, now this is the same as Ka because it's a weak acid. The only difference is I'm writing H3O plus instead of H plus, but as I keep stating over and over, H plus, H3O plus are the same thing. All right, so it doesn't matter which way you write the reaction. All right. However, if you're going to label all conjugate acids and bases, now you have to write it in the way that we have it written here. So HF is your acid, all right? And so up here you have your acid, but you don't have a base, all right? But the base is water. So if it says label the conjugate acid-base pairs, now you have to write it with water being the base. HF is your acid. All right, and so we see that H3O plus, that is always an acid, and F minus is a base. It doesn't have any H's to be an acid. And so we have our conjugate acid-base pairs. We have our conjugate acid-base pairs. They just differ in one H plus. All right, so here we have HF, which is a weak acid. HF is a weak acid. All right, and so H3O plus, so you have your 6 strong acids, but then right below that is H3O plus, because H3O plus is what you get when you add acid, strong acid, to water. So H3O plus is also a strong acid, but it is not an acid because all acids are neutral. This is an ion. But anytime you have H3O plus, that is a strong acid. All right, so this, anytime you have H3O plus, that's a strong acid. Anytime you have OH minus, that's a strong base. And so you will always get in a Ka, always a product is H plus, always a product, or H3O plus, again, same thing. And that is always a strong acid. And so the equilibrium will always shift to the left anytime you have an equilibrium. If you don't have an equilibrium, all right, as you had with the HCl, no equilibrium, of course, then you don't have to worry about that. All right, but for all of your equilibriums, you're forming a strong acid. All right, and so the reaction always favors the weaker acid, weaker base. For every Ka, the weaker acid and weaker base is on the left. All right, and so always for your Ka, your weaker acid, weaker base is on the left. Strongers are always on the right. And that's why it favors reactants. Very few products, mostly reactants. Products over reactants, always a small value. All Kas are small because you have your weaker acid and base as reactants, stronger acid and base as products. Every single Ka. All right, so let's solve our problem here. And so we have x squared over 0.10 minus x is equal to the 6.8 times 10 to the minus 4. All right, so we just plugged in our x and our x. That's x squared. And then our HF was 0.1 minus x. Again, you can do the quadratic. It works fine. I feel like there's a lot more math errors. I will always do successive approximations. Every time you have a Ka, it's going to be small. You can always neglect x, but you got to plug it in to see if you have the final answer after 1 or if you have to do it again. All right, so we have then x squared over 0.10 is equal to 6.8 times 10 to the minus 4. Multiply both sides by 0.1. Take the square root. X1 is 8.2 times 10 to the minus 3. All right, so now you got to check that. So you plug it in. So now you've got x squared over 0.10 minus 8.2 times 10 to the minus 3 is equal to 6.8 times 10 to the minus 4. All right, so you subtract those, multiply both sides by that, and then take the square root. X2 is, again, this is always going to be the highest number you get, and X2 is always going to be the lowest, 7.9 times 10 to the minus 3. Plug that in, x squared, 0.10 minus 7.9 times 10 to the minus 3 equals 6.8 times 10 to the minus 4. And you will get that same answer again. Right? And so you have 7.9 times 10 to the minus 3. That then, so that is the same as this. That means you're done. You circle that. That's your answer for x. And x is the concentration of your H plus. All right, so you have your HF, which was 0.10 minus the 7.9 times 10 to the minus 3. All right, and then your H plus, that is 7.9 times 10 to the minus 3. And your F minus, which was X, 7.9 times 10 to the minus 3. All right, and when you subtract this and you have 2 decimals minus 3 decimals, 4 decimals, you've got your answer to 2 decimals, and that comes out to be 0.09 molar. All right, but what we wanted was the pH. And so the pH is equal to the negative log of 7.9 times 10 to the minus 3. And when you push the buttons on your calculator, you get 2.10. All right, so we had our 2.1 concentrations, and we said that the HCl is more acidic and would have a lower pH. So 0.10 molar HCl, that gave us a pH of 1. And then our 0.10 molar of HF, which is a weak acid, gave us a pH equal to 2.10. All right, so that is a higher pH, that is less acidic. All right, so the other question that's going to be asked is to calculate your percent ionization. To get your percent ionization, it is simply the amount that went to the right, x, minus your initial, the amount that could have gone to the right, times 100. So we know the answer for HCl. We know it's 100%. Why is it 100%? Well, because the X value for HCl was 0.10. The initial concentration for HCl was 0.10 times 100. That gives us 100% ionized. That makes it a strong acid. That is the definition of a strong acid, 100% ionized. All right, so if it's not a strong acid, it will not be 100%. It will be less than 100% ionized. And so if we do, so this was your HCl, if we do our HF, the X value, 7.9 times 10 to the minus 3 over your initial concentration, 0.10 times 100, you get 7.9%. All right, so the percent ionization for HF is 7.9%. Now, another interesting question that on the test may not give you enough information to solve it with a number is to calculate, mine's going to say calculate the pH of 1 molar HF and percent ionization. All right, so the question could be of HF the same thing, except I'm not going to give you any numbers to calculate it. So what it would be is, well, which is a stronger acid, 0.10 molar HF or 1 molar HF? So more concentrated is more acidic. All right, so I'll stick my hand in 0.1 molar acid. You give me 18 molar acid, yeah, it'll dissolve my hand. So anyway, so the lower the concentration, then the less acidic it is. All right, so this is more concentrated, more H plus, more acidic. And so you would say that this is going to be your stronger acid, so lower pH. So what you can say is, well, it's going to be less than what we got before. So it's going to be less than 2.10. All right, so then it's going to be percent ionization. So here's one where we're going to calculate it, and then I'll tell you that this is always going to be the case for every example. All right, so let's do the pH first, HF. All right, now you don't have to look up the Ka because it never changes. It is a constant. The Ka for this, 6.8 times 10 to the minus 4. We are not going to be changing temperatures. We are going to stay at 25, use the same K values. So 1 molar, 0, 0. All right, so minus X, plus X, plus X. At equilibrium, we have 1 molar minus X, we have X, and we have X. So we have X squared over 1 minus X is equal to the 6.8 times 10 to the minus 4. Exactly the same thing we did before, except last time we had 0.1 molar, and this time we have 1 molar. All right, so we do successive approximations. We neglect this X value, and you get X squared is equal to 6.8 times 10 to the minus 4 because it's over 1. We neglect the X. Then we take the square root, and we get 2.6 times 10 to the minus 2. So x1, 2.6 times 10 to the minus 2. We plug it in. And we get the same thing again. So when we plug that in, we have our x squared over 1 minus 2.6 times 10 to the minus 2 equals 6.8 times 10 to the minus 4. X2 is exactly the same. X2 is a 2.6 times 10 to the minus 2. If it were 3 sig figs, it would not have been the same. This is 2.6 something, that was 2.5 something. But they both rounded to 2.6. And so 2 sig figs is all we had for Ka. It's all we need. And that is our value for H plus. So now we know X, 2.6 times 10 to the minus 2. So then we just take the pH. That is the negative log of 2.6 times 10 to the minus 2, which is a 1.5 something, I think. I'll push that again. Negative log of 2.6, 1.59. So the pH here is 1.59, which is what we predicted. That is less than we had before, 2.10. Now for X divided by initial times 100% ionization. That is 2.6 times 10 to the minus 2 divided by 1 times 100. This is a 2.6%. So your percent ionization is 2.6%, all right, for 1 molar. It was 7.9% for 0.10 molar. So that is always going to be the trend. Your percent ionization will always be higher when you have a low concentration, because how do we find it? We get X and we divide by the initial concentration. If we increase the initial concentration by a factor of 10 in this case, from 0.1 to 1, we did not increase, we will never increase the X value by that amount. All right, so the higher the concentration, you're dividing by a larger number, you'll always get a smaller percent. So that could be a question without any numbers given. Which one of these would have a higher percent? A 1 molar or a 0.1 molar, the higher percent is always the lower concentration. I'm going to make videos for the lab and put those up. And I'm also going to put the your grades in Moodle by Wednesday. And then on Thursday, you can see your exam.